Assalamualaikum, good morning and hi. My name is Nur Fatihah binti Uthman. I am the first presenter for a group 4. So first of all, I will introduce my team members. First, Azamuddin bin Saidin. Second, Muhammad Ajwa Azrai. Third is me, Nur Fatihah binti Uthman. And fourth is Lizzie Ming. The title of our experiment is a performance evaluation of rubber blend, plastic rubber blend and plastic blend. So this study on the influence of a blend ratio of the polymer blend. So what is the polymer blending? Basically, polymer blending is the process of mixing two or more polymer to create a material that is better than what you will get from one polymer. So, by blending, we can combine the strength of each polymer. For example, one polymer might be a super tough, while another one could be a flexible or resistant to chemical. When we mix them, so we can get the best both properties, which that is creating a material that is stronger and more flexible or even more durable. So in our experiment, we try out different blend ratio to see how they will affect the final properties of the material. The objective of this experiment is first to differentiate between polymer composition by considering their blend ratio, properties, homogeneity and characterization technique. Second objective is to investigate the relationship between blend composition and its impact on mechanical properties. Objective 3 is to evaluate the influence of blend composition on thermal and processing characteristics.
Let's explore some of the common challenges faced during the development of polymer blend. Challenge 1. Mechanical properties. Different blend ratios result in varying mechanical properties. This is because change in the intermolecular interaction between polymer change directly affect how well the material can withstand force like tension, compression or bending. Additional, phase morphology, how the component distribute within the blend, also influence this mechanical outcome, and unbalanced ratio could lead to weak spots, making the material less reliable or for application requiring structural strength. Challenge 2. Phase separation. When blending polymer that are not fully compatible, phase separation can occur. This means that the different polymer might not meet uniformly, leading to distinct domain within the material. Phase separation typically weakens the mechanical properties and compromise the overall performance of the blend, as it can introduce defect or discontinue that the limit material strength and durability. Challenge 3. Thermal and processing properties. The ratio of polymer also affect thermal and processing properties. Variation in molecular interaction and phase morphology during processing can alter melting point, viscosity and crystallization behavior. This becomes a significant factor during manufacturing, while controlling these properties is essential for achieving optimal material consistency and quality. In lab 1, we are working with a plastic blend formulation that combine two thermoplastic and a compatibility agent. The blend include polypropylene PP, a strong and flexible thermoplastic used at 20 part per 100 rubber PHR with a weight of 38.83 grams, and low density polyethylene LDPE, a flexible and chemical resistant thermoplastic that back up 80 PHR weighing 155.34 grams. To ensure proper blending of two polymer, we also use a compatibility agent at 3 PHR with weight of 5.83 grams. This brings the total formulation to 103 PHR and 200 grams in weight. The goal of this blend is to achieve the material that balances the flexibility of LDPE with the strength of PP, while ensuring good compatibility between the two components. In polymer testing and processing, we use a variety of specialized machines to evaluate the properties and performance of material under different conditions. This machine help us understand how polymer will behave in real-world application, ensuring they meet necessary standard for strength, durability, and chemical resistance. Today, I will walk you through the key equipment we use, explaining their role in the testing process and why they are essential. The hot press is used to mold the polymer material and by applying heat and pressure. First, the plate are preheat to specific temperature, and then the material is placed between them where it is pressed and allowed to cool, solidifying into the desired shape. The extruder melt raw polymer pellet and push the molten material through a die, forming continuous shape like sheet or film. After exiting the die, the material is cooled and cut. The instrument machine tests the mechanical property strength of material by applying a force that stretches or compresses a sample, recording its deformation and providing data on strength and flexibility. In the oven for aging, polymer samples are exposed to control the heat to stimulate long-term environmental exposure, helping evaluate changes in properties like hardness and flexibility over time. The swelling test submerge a polymer sample in a solvent to measure how much it expands or swell when exposed to liquid, providing insight into a chemical resistance. Lastly, hardness testing involves pressing a durometer against the material surface to measure the resistance to indentation, with multiple readings taken to ensure accurate result.
Assalamualaikum. Today I want to present about lab plastic rubber blend (TPE). The rubber we use is EPDM and PP ratio of 50-50. Why we use EPDM? Because it's good in flexibility and elasticity that we can see the elongation. So we use a PP because it have a good stiffness and strength. So we can mix blend together, can see the tensile and elongation where is a slightly drop. Uh, okay, then we have a activator. Activator we use a zinc oxide and stearic acid for the curing agent, active the curing agent. Then we have a accelerator TMTD and CBS. Then we have a curing agent that is a sulfur that we use a 3-PHR. And then we have a filler calcium carbonate and coupling agent maleic anhydride that we use a coupling agent for the binder combination of PPDM and PP. So sulfur we use a 3-PHR that's mean is a polysulfidic formulation that is CV formulation. Okay, for the material preparation, first thing we need to do the material preparation before we do master batch. After the material prepared, we can use two roller for do the master batch of rubber compound. Uh, for the master batch, first we don't put the sulfur as a carrying agent because if we put the sulfur first in beginning, for after that we use the heater mill. The heater mill will make the rubber is cure in the machine. So we don't put sulfur at the master batch. Then when the master batch was done, we put a little bit of a master batch. Then we put in the heater mill to blend with a plastic. So the temperature plastic we use in the heater mill is a softening point or a melting point of the plastic. Then after plastic and rubber blend together and done, then we put back into the two room to put the curing agent sulfur. Then we put the sulfur to make a rubber cure. have pre-cure. Okay. Then after the rubber compounding done, we put a little bit like 60 gram, uh, 60 gram or little bit to use in a remitter to get a T90. Then to get the T90, the temperature that we can use in the hot press. Then we use the hot press to make a rubber cure to make a dumbbell shape. From the hot press, we have the sheet. Then from the sheet, we can do a dumbbell shape. Dumbbell shape, we use a ASTMD 412. Then we have a two sample, aging and unaging. For we use oven for the aging. In 1 week, I think, for the oven. Then oven is we use a ASTMD 2505 for aging. Then after we have a two sample, we use an instrument machine for the tensile strength, uh, flexural and others. So from the instrument machine, we use a ASTMD 412, and we have also use a test for hardness. Hardness we use a ASTMD 2240, and we use a show A to get the hardness. Then we have a swelling. We use a STMD 2335. That's means for liquid. And we have a toluene and oil, cooking oil and like petrol gas. Okay.
Okay, and then my turn will be talking about formulations of lab 3, which is rubber blend. So here is the formulation of the rubber blend. So the rubber we pick will be natural rubber and synthetic butadiene rubber, followed by activator with zinc oxide and stearic acid. Accelerator will be TMTD, CBS, while the carrying agent will be sulfur. Filler will be calcium carbonate. So the total weight of the total compound will be 200 grams. So here we did our calculation and measured it based on their pHR. So each material is stated with the individual specific weight. So the basic procedure of it is starting with material selection and material weighing. So after weighing, we'll proceed with the milling of rubber. So we will start milling of rubber with of natural rubber and followed by synthetic butadiene rubber. So after they mix, and with around 3 to 4 minutes, and then we'll be adding. First, we'll be adding the filler calcium carbonate, which is 42.86 gram. So why is calcium carbonate added first? So calcium carbonate is added first to ensure that it is dispersed efficiently within the rubber matrix to ensure a uniform mechanical properties. So after calcium carbonate is added in, we are followed by zinc oxide, which is an activator that works well together with stearic acid to accelerate the vulcanization process. And this makes the compound easier to process. And then will be followed by TMTD, an accelerator, which is to prevent scorching. While CBS is added after TMTD, where CBS is an accelerator that allows faster curing when heated and also maintain the scorch safely. And last but not least will be sulfur. Sulfur will always be added last in a rubber compound as sulfur is a vulcanizing agent. It forms cross-linking between rubber polymer change and premature vulcanization or even scorching. So here are a few general expectations that we expected to hit after our lab session. So first will be to gain a deeper understanding of how blend composition influence various properties, including mechanical performance, thermal characteristic, and processing behavior. And then will be to identify optimal blend ratios and composition for achieving specific desired properties in different polymer systems. Plastic with plastic, plastic with rubber, and also rubber with rubber. And last but not least, our expected result will be development of effective characterization techniques to accurately assess blend composition, homogeneity, phase behavior, and material properties.